Okay, so welcome back after the break. Um, I think most people, barring 2 or 3, have done the midterm. I'm not going to talk about the midterm until everybody's done it. Once everybody's done it, that should be next week. I'll do a recap of the midterm. Um, One thing I think I've said to a lot of people, but I don't think I said to everybody, is think about the midterm as practice for the final, right? So if you're not happy with the grade you got on the midterm, what I'm going to say is if you do better on the final than you did on the midterm, I will replace your midterm grade with whatever the percentage was that you get on the final. Okay? And actually that usually doesn't affect that many students, but it usually in a class this size, 2 or 3 students sometimes do better on the final than they did on the midterm. So, okay. We're going to change gears now, and I'm going to talk about impedances rather than resistances. It's the same thing, except impedances are complex valued. Right? So I need to talk a little bit about complex numbers. How many people are okay with complex numbers? Got a couple of people? You're okay? So complex numbers are basically a way of encoding, instead of the real number line, just a line. Complex numbers are a way of encoding the 2D plane, right? The x and the y axis. That's one way to think of them. And so let's just see where we are. I think I moved that for some reason. Didn't actually mean to. There we go. So that's where we are. I'm hoping to do the superposition lab today. And I just realized I don't think I actually have a lab called Introduction to the Oscilloscope, so we might move the phase relationships up one. So we've got 1, 2, 3, 4, 5, 6 sessions left. Apart from transients, you're not going to hear anything new. The only new part I'm going to be talking about for the rest of the course is doing everything we've already done, except with complex numbers, complex impedances, instead of real valued resistors. Okay? So all the mesh analysis, nodal analysis, superposition, Thevenin and Norton, well, let's go through the list. Ohm's law, parallel circuits, series circuits, Kirchhoff's current law, Kirchhoff's voltage law, voltage dividers, current dividers. Everything there applies exactly the same way, except there's a little bit of a jump from representing, now instead of constant voltages, we're going to be dealing with sinusoidal voltages at a particular frequency. It's a little bit of a jump from there to complex numbers, but it's only a relatively small jump. Before I go into impedances, though, I'm going to go through some slides about complex numbers. Let me get my pen out. Alright, so I want to do that background on complex numbers. Alright, topic 4. Okay, so that one. So, as I said, a complex number you can think about just as a way of representing a 2 vector, a way of representing a point on a 2D plane, the xy plane, or as I'm going to call it, the real and imaginary plane. Now, I'm going to be confusing even the people who are very happy with complex numbers, because I'm going to be using j to represent the square root of -1. Right? The reason is because I'm an electrical engineer, and electrical engineers, as you've noticed, use the symbol I to represent current. Right? So we tend not to use I for the square root of -1. Sometimes we do, sometimes it makes sense depending on who you're talking to. Right? So I is the square root of -1, but I'm going to be using j. So when I plot a point here, right, in xy coordinates, this is just 1, 1, but the way I would write that out is as 1 plus j, or maybe 1 plus 1j, to be clear that it's that the magnitude in the imaginary axis direction is 1, the unit. Now, one thing we're interested in is, in real life, there's really no such thing as an imaginary voltage. Right? I can't get a multimeter out and put it on the imaginary voltage axis and measure imaginary voltages. So the mathematics we're going to use to describe these circuit behaviors use complex numbers. But in reality, when we come down to measuring voltages, the thing we're looking at, the thing we measure, is the projection of that imaginary number onto the real axis. Right? So in this case, if I have this blue vector here, right? So that's going to be 1 plus 0j. The projection of that 1 plus 0j onto the real axis is just 1. Right? So that's why this is plotted here. So if I measured this complex valued voltage with my voltmeter, I'd get a 1 on it. If I then rotate that unit vector by 45 degrees, right, so now the number is 1 on root 2 plus j 1 on root 2. Now, the projection of that vector onto the real number line is 1 on root 2, 0.707. right? So I get that value instead of 1. And I can continue rotating that around if my number is 0 plus 1j, right? The projection of this number onto the real number line, this complex number onto the real number line, is 0. And I can continue rotating it around. So what we get out of it is, I think there might be another one there. There we go. We get in this case, it's a cosine wave. Cosine starts off at 1 at the 0, the x equals 0 position. So that's a cosine wave. So that's just my my explanation again, that I'm not going to use I, that should be a small I, I'm going to use J, because we've been using I for current throughout this course, so I'm going to be using J from, and one partial justification is if you ever use 3 vectors, usually the unit x-axis vector is I, the unit y-axis vector is j, and the unit z-axis vector is k. So that's my justification, partial justification for using j for the y-axis. And so you can draw a complex number as a 2 vector, as a vector on the plane. Okay. Now this one, probably the scale should be squared up. The y-axis scale is contracted compared with, well, the x-axis scale is expanded compared with the y-axis. But this number here is just -3. This number here is +2. I don't know whether I can get an orange maybe. And this number here, I don't know quite what it is, but it's probably, I don't know, so it's about -2.3 and plus j 3.5 or thereabouts. So there's lots of ways to represent complex numbers. One way is the way I've been drawing it so far, right? I've been using Cartesian coordinates. Right, x, y. Another way to write almost the same thing is x plus jy. Sometimes that's worthwhile, but sometimes you're better off specifying an angle and a direction, an angle and a magnitude. Right, so instead of 0.707 plus j 0.707, which would be the Cartesian or rectangular way of writing, you might be better off saying that that's 1 angle 45 degrees. Okay, so we split it up into the magnitude of 1 and the angle that it makes with the x-axis going in the counterclockwise direction. Right, so right? So that's the positive angle direction, is the counterclockwise direction. Now there's another form that maybe is a little bit more useful, so particularly when we're thinking about converting from rectangular form to polar form, and that is this exponential form. To write that same number, 0.707 plus j 0.707, I can write that as 1 times e to the j. Now, your calculators allow you to work in degrees or radians. However, there's an inconsistency with most calculators. If you have your calculator put into degree mode and you do cosine of 45, that will give you 0.707. Unfortunately, if you do this, and it's wrong, so don't write this down, if you do this, that's not going to do the same thing. What you have to do, if you're writing angles in exponential form, is you have to write it in radians. Okay? So, pi over 4. I recommend that you keep your calculators in radians mode, not in degrees mode. You may want to be able to convert from radians to degrees, but that's just dividing by pi and multiplying by 180, right? There's 2 pi radians equals 360 degrees. Or pi radians equals 180 degrees. Now, why am I telling you this? Well, like I said, it means that you can use Euler's formula. I think the guy's name's up there. Yeah? So Euler's formula. You can use Euler's formula to convert from one to the other. Because Euler's formula says that e to the j theta is equal to cosine theta plus j sine theta. So now you can write, if you have your complex number in polar form, you just have to plug it into Euler's formula to get it into rectangular coordinates or Cartesian coordinates. A cosine theta is the real part, and a sine theta is the imaginary part. Where a is I don't know whether it's written, but this, I would write the complex number down in polar form as a angle theta. And that sort of tipped over less than sign is what I call an angle. This bottom thing here should be flat, horizontal. So that goes one way. But we can go the other way as well. Right? So I'm hoping that you remember that some of your trig identities, right? And one of them is that sine squared theta plus cosine squared theta equals 1. So a way to look at if you multiply a complex number by its complex conjugate, right, I'm going to get a half plus a half and then 0. So if I have a plus jb and I multiply that by a minus jb, that's the complex, oops, that should be a b. Let's erase that. Right, this is the complex conjugate. Then that's a squared plus b squared. Right? So in order to get the magnitude, I just have to take the square root of it. So if I have a plus jb, and I want to get that into the form, I probably shouldn't have used a and b. Let's call it c angle d. Then c is the square root of a squared plus b squared. And d equals arctangent of b on a. Now there's a slight problem with that definition of finding d, because it's not 4 quadrant. Right? What I mean by 4 quadrant is if you take the ratio of b to a, you can't tell which quadrant it's in, which quadrant the thing is in. So the angle you will get is only in the left half plane. Right? There are other ways. If you're using MATLAB, there's a function called atan2, which takes 2 arguments, and that will give you a full 4 quadrant angle. But this one here, that's only 2 quadrant. If you know that your angle is in the right half plane, then it's okay. But if you don't know, so if a is positive, then you know it's in the right half plane. So you can just use the straight arctan function. So let's just write that down. So here we've got the, let's go back to that one. Right, rectangular, a plus jb, polar, r angle theta, exponential r e to the j theta. And remember, this is in radians. If I write this one down, I will often give you the angle in degrees. So be very careful that you know that it is in degrees and that you're working in radians, or vice versa. So then, to convert this way, we need that A equals R cosine theta and B equals R sine theta. And to convert the other way, we get that R equals the square root of A squared plus B squared, and theta, I'm going to write it down as A tan 2, the MATLAB thing, just to remind you that it's, if you need it to be 4-quadrant, then it's got to be a 2-parameter method. So there's yet another problem. Right? Most of you have TI-83 or TI-84 calculators. They're good calculators. They have one fundamental flaw for this course. That fundamental flaw is, even though they'll let you do matrix operations, they won't let you do complex matrix operations directly. Right? So you can edit the matrix, but you can't enter 1 plus j into any of the elements. You can only enter a real valued number. However, all is not lost. It just gets a little complicated. What you can do, and there's a video here that I'll show soon. I might move over there, and because I think there's a bit of a lag if I play video here, but we'll try it. So if I have a complex number a plus jb, and I need to put that into a matrix, I can't just put it into, in fact, let's do this. Let's do a 2 by 2 matrix. C plus jd, d, e plus jf, and then g plus jh. Right? For those TI-83, TI-84 calculators, if you've got a TI-99, it lets you do that. But what you can do is you can convert that 2 by 2 complex valued matrix into a 4 by 4 real valued matrix. Alright, and all you do is replace each complex number with a 2 by 2 matrix. And now you can plug that matrix into your calculator, and you can do RF or matrix inverses or whatever takes your fancy with it. And the answer you will get is in this will have the same pattern, right? In your RF, right, instead of getting 1, 0, 0, 1, I don't know, let's go X, Y. Actually, let's just do it. Instead of getting, if the answer would be that, if you could enter complex values into your matrix, what you'll get is what you might expect. Something like that as an answer instead. If you don't get something with that sort of a pattern, then there's something wrong. You probably entered something incorrectly up here, so this pattern wasn't followed. Okay, let me just show that video. It does a better job of it than I do. Let's see if we can. That's the one. And it's gone off there, so let's...
J is the square root of -1, which is sometimes called as I. X and Y are two unknowns. And like the real case, you can just take the coefficient matrix here and change this into AX equal to B type matrix equation. Now, if you want to solve this using the RREF method, you should put these two matrices into a single matrix like this, and then all you have to do is just plug this into your calculator and do the RREF if you have TI-89. Now, the trouble with TI-83 is that you cannot put, it doesn't allow you to put complex numbers into matrices. So you have to do this very complicated way of solving the equation using real matrices. And at the end of the video, I hope you can manage it, or you might just decide to buy a TI-89. Okay, but let's see how it goes. Now, the key to changing a complex matrix into a corresponding real matrix, so you can just plug this into the calculator to solve, is to change a single complex number into a 2x2 matrix. How do you do that? Well, first think about this 3 plus j as 3 plus 1j, and put those two numbers 3 and 1 as a column vector. So you have 3 and 1 up and down. And then you have to put another column right next to it, and the way you do it is you flip these two numbers. 3 and 1 gets flipped into 1, 3, and then you have to negate the top one. Okay, so you have to, and you have to do this for every one of these elements, even if the number is real. So what it does is it doubles the size of the matrix, both rows and columns. So this is a 2-row and 3-column matrix. Therefore, after this process, you will end up with a 4-row and 6-column matrix. So you will have a huge matrix. That's why this method is so complicated. Okay, let's move on. This.
Okay. So I'm not going to go through the whole thing. I suggest you have a look at it.
Okay, let's see how.
Have a look at it yourself. Let me just make sure it's available on Blackboard. Oh, there we go. It looks like it's there already. Right, so it's under topic slides, and this video gives an example of how to solve. That's the same video. And I'm just going to put that there, maybe. There we go. Let's just see if we can move it down out of the way. Okay, so that is a brief background in complex numbers. Right? As I said, we're going to start using them now because I'm going to introduce some more devices. See if I can find a couple. Do that one. And I think the other ones might be over here. Let me just check that. There we go. Okay, so I'm going to, you might have a hassle passing them down. So I'm going to hand out 3 different things. Okay? And these, once you're done having a look, I'll take it down to AJ. There we go. So these 3 things are 2 capacitors and an inductor. Right? The capacitors are the big orange one and the cylindrical light blue one. And the black one, which you should feel is a little bit heavier than the others, is an inductor. So the inductor is a bit heavier because it's basically just usually a ferrite core. Ferrite is a material with nice magnetic properties, and it has wrapped around it a lot of wire. So, and we'll get to this on the other slide. So the inductor circuit symbol is just that, because that's all it is. I once did I once made a circuit that was operating at quite a high frequency, and I calculated the inductance that I needed, and I had to basically make a wire that was 2 or 3 turns for the inductance that I needed. The capacitors are a little different. Those 2 capacitors are different sorts of capacitors. The orange one is what's called a ceramic capacitor. and the blue one is electrolytic. So the ceramic one, as the name suggests, is made up of a ceramic and usually some sort of conductor. Sometimes it's carbon. And the way you draw a capacitor circuit-wise is like that. Because all a capacitor is two conducting plates separated by some sort of electrolyte. In the case of the ceramic capacitor, the electrolyte is a ceramic. In the case of the electrolytic capacitor, the electrolyte is, it depends, it's either a fluid or a gel. Usually it's a gel these days. I will warn you, it won't happen, but just be careful. I think those electrolytic capacitors are done the same way. Yeah, right. So see there's a cross on the top? So have a look, there's a cross on the top of the... That's because if you treat electrolytic capacitors incorrectly, they will explode. Right? And the cross is etched onto the top of the capacitor, so we know what direction they're going to explode in. Okay? Now, it's relatively difficult to get them to explode. You will also notice on the electrolytic capacitor that on one side of it there should be a darker stripe with a minus sign going through the stripe, I think. Sometimes it's got a plus sign, but usually it's a minus sign. Electrolytic capacitors are polarized. So if you're putting them into a circuit that uses direct current, a constant voltage, they need to have that negative leg connected to ground and the other one connected to a higher voltage, a positive voltage. Most of the circuits we're going to be using them in, we're going to be using them in alternating current, so it doesn't matter so much. The reason they explode is usually because those also have a voltage rating, which is probably 16 or 25 volts. I've forgotten what these ones are. If you connect up 50 volts DC to them, they will explode if their voltage rating is 25 or 16 volts. Okay? Yes, when the gel ones explode, the gel ones in some ways are worse because the gel is stickier than the fluid, right? So if you get in the way, the gel sticks a bit more. It won't happen. I'm just making sure you're aware that sometimes these things happen. Okay, so let's try and relate what I just talked about as far as complex numbers are concerned to those devices you've got. So So this is wrong. I keep getting the wrong one. This should be impedance. I thought I fixed that. I've been toying with the idea of teaching this course from scratch, never using the word resistance. right? Because what I'm going to be using now instead of resistance is impedance, because impedance is much more general and is more used in practice. So, as I said, we're going to start using complex valued impedances, and I'm going to start referring to this part of the complex value as the resistance, and this part of the complex value as the reactance. And together, they're the impedance. So let's go back to square one. Go back. Sorry. So let's go back to square one, right? Except we're going to take a slight left turn, and instead of using constant voltages, now I'm going to start using cosinusoidal or sinusoidal voltages. Okay to continue? Yeah. So here's a circuit. We have a voltage source, a current, and a resistance. Instead of just being a voltage source at a level A, we're now making the voltage source a function of time. And it's going to be A cosine omega t plus theta. So this little W thing here is a small omega, and I really find it funny that I call it small omega, right? I don't know if you've probably heard, you might have heard omega before. You've probably heard omicron before. In Greek, that's just little o and big O, right? So calling this little omega seems a bit strange. But we use big omega, right, for the ohm symbol. And we use small omega for frequency, and this is what I call theta. Now we know Ohm's law applies in this, so we can just do V equals IR. The only difference between this V equals IR and the V equals IR we've done before is the voltage changes. It doesn't matter. It just means the current changes to match. Right, so we can, if we apply our A cosine omega t plus theta volts, what we get for our current is A cosine omega t plus theta divided by R, amps. And this is a little bit of circular reasoning, but then we can put V on I, V of t on I of t. Now we're going to do a slight, notational shift, and we're going to rewrite cosine omega t as just one, cosine omega t plus theta as one angle theta. It's just a notational shift. If we do that on both numerator and denominator, then, as I said, it's a little bit circular, but we get back the impedance. Right now, because we're talking about a sinusoidal voltage and a sinusoidal current, or cosinusoidal, now we're talking about impedance. But in this case, the impedance is just the resistance. There's no reactance, there's no complex component, there's no imaginary component, rather. So capacitor. Now we've just taken the resistor away, and now we've put in a capacitor. If instead of a sinusoidal voltage, I just put a constant voltage, that circuit, the capacitor, is just two metal plates separated by an electrolyte. So for direct current, for constant voltage, no current flows. It's a gap. Right? It's only when the voltage alternates or changes that something different happens. So here now, if we apply a cosine omega t plus theta, the relationship we have between voltage and current for a capacitor is a bit different. Right? It's not V equals IR. It's I equals C dV dt. Right? So the current is proportional to the rate of change of voltage. So if I know that, I equals C dV dt, I can take my A cosine omega t plus theta, and I can take dV dt and get minus A omega sine omega t plus theta. So then I can figure out what the current is. It's just C times that. C dV dt. And then I can go through the same notational shift that I used for the resistor. Right, I'm going to want to find out what the thing I'm aiming to find out is the impedance of the capacitor. And the impedance in any event is always voltage divided by current. So I can take my A cosine omega t plus theta volts and divide it by my C dV dt, which is minus A omega c sine omega t plus theta. And then I know the relationship, the phase relationship between cosine and sine. So I can replace my sine omega t plus theta with a cosine omega t plus theta minus 90 degrees. And that lets me now do my notational shift. So this is nothing more than 1 angle theta minus 90 degrees. And this is the same as we had before, 1 angle theta. And then I can rewrite that as, well, eventually it's just going to be, this is going to be 1 angle 90 degrees, right? Because you can, the two thetas cancel out, and the negatives cancel out. Let's go with blue. So we're just left with this, or eventually 1 on j omega c. So that gets our impedance of a capacitor. So remember, a capacitor is just that, right? The circuit symbol pretty much matches the way it's built. If you connect up a DC constant voltage source to it, that capacitor will charge up. If you disconnect, after that's been connected for a while and then you disconnect the voltage source, the capacitor is still charged up. There are things called supercapacitors that are basically sometimes used in place of batteries. If you get the right supercapacitor, you can charge those up to very high voltages. They don't contain much energy, some, but you can charge them up to very high voltages. If you charge them up to very high voltages and then you touch the pins, you will get zapped. Back when I was in high school, I was in the electronics club and we had some supercapacitors. We also had a kid who he kept picking pockets, which was really annoying. So what we did is we got some of those supercapacitors and got I think it was about a 1 kV supply. We charged them up and left them in our outside pockets charged up. He learned pretty quickly not to pick our pockets, right? You might have been told about computers, right? And you've been asked to power them down and power them back up again. You know, have you tried turning it on and off again? What you may not know is these things have capacitors in them. And oftentimes you're asked to turn it off and leave it off for some time. before turning it back on again. The reason is because of the capacitors. Instead of this sort of, effectively this is what's happening, but what you've effectively got inside your computer is that. So when you turn off the voltage source, you don't have a disconnected capacitor, you've got a capacitor that's connected to ground via a resistor. So what happens is the charge slowly dissipates. Right? And you may have probably turned off some electronics at home, maybe even unplugged it, and you can still see the LED glowing for a while, right? That's what's happening. Eventually that capacitance is going to be discharged and the voltage across it is going to disappear, and then you eventually get lights out. Okay. So as I said, inductors are just, let me grab those bits if I can. Is there another capacitor? I think down that way. Okay. Thank you. You got there? Okay. Thank you, sir. Yeah, so those inductors are just like the diagram, right? They're a little bit different. They've got sometimes the way these are drawn, particularly if they're a particular thing called a choke, particular sort of inductor. Sometimes they have lines running down the middle, right? And that would be what's called a choke. So what I'm looking for is a USB cable. If you see a USB cable, sometimes it's on power cables as well. Can't see any USB cables. If you see a USB cable with a little plastic coated cylinder on it, that's a choke. And it's aiming to reduce electromagnetic interference between one end of the USB cable and the other. And all the choke is a sort of inductor. It's usually particularly designed. Chokes are usually tuned to whatever the mains frequency is. So 60 hertz here, and it's to get rid of any mains hum on the data communications on the USB cable. Mostly you don't need them. Usually just some shielding's enough. But sometimes you need a choke, particularly in a lab environment where there's lots of stuff happening. Okay, so again we're going to apply, actually before we do that, if we just apply our constant voltage source to an inductor, it's just a short circuit. Right? Inductor is just a wire. It might be a very long wire, but it's just a wire. So it has very, very little actual resistance, real valued impedance. So this is the same as a short circuit. If it's not constant voltage, if it's a an alternating current, then this is the relationship between the current and the voltage. I equals 1 on L integral v dt. The other way to look at that is v equals L di dt. And that v equals L di dt, if you drive a gasoline-powered car, that's the thing that's keeping it going. Right? Newer cars use the electronic version, but older cars used to have a thing called a coil. And the coil is connected to the distributor, and the distributor is the thing that sends the spark to each of the spark plugs. The way that spark gets generated in older cars, it's done electronically now. But the way it's done in older cars is through a thing called points. Right? And points are nothing more than two pieces of metal pressed together that all of a sudden are made to pull apart. If you've got current flowing and all of a sudden you open the switch, that makes di dt go very big very quickly, which makes v go very big very quickly. In order to make that spark on your car's engine, you need that high voltage to bridge the gap between one side of the spark plug and the other side, in the center. Right? So that's pretty important. It's also why you shouldn't ever unplug something from the wall if it's still going. Right? Because you're going to get L di dt. That's why you'll get a big spark if you do it. Mostly. Depends on the exact amount of current and how well it's up. But you can get a spark just by unplugging something without turning it off first. That's why I've always been a little hesitant about US mains plugs. In Australia, the code is that you have to have a switch on each of the mains plugs. So you can turn it off. Know you turned it off before you unplug it. Okay, so we can do the same sort of thing. We've got a relationship between voltage and current. So we can do our, apply our voltage. There's our voltage, A cosine omega t plus theta. So there's our current after we pass it through the integral. So I of t is A on omega L times sine omega t plus theta. So then we've got our ZL. And we can do the same shift here from sine back to cosine with the phase shift. And we use our notational shift from cosine omega t to cosine omega t plus theta to 1 angle theta. You'll notice something a little strange about that notational shift. The strange thing is, I've dropped the omega. Right? Okay, it's still there in front of the L. But the thing is, if the circuit we're using is running at omega t, everything is running at omega t. So the only reason we need to know omega is to calculate ZC and ZL. So a lot of the questions you'll see in this part of the course won't necessarily mention cosine omega t. They may only give you A angle theta as the voltage or the current. Anyway, then you can, after that notational shift, you can eventually figure out what the Z impedance is. Sorry, the inductive impedance is, and it's J omega L ohms. Again, it's purely imaginary. If you've got a DC current, doesn't matter. It's like a wire, so there's no impedance. Notice if you've got DC, omega is 0, right? So the impedance is 0. Notice back here, if omega is 0, the impedance is infinite, right? Because it's just a gap, which is what you'd expect. So that's the summary. Resistor, inductor, capacitor. The resistance R for the resistor and nothing for the others. The reactance, the imaginary component, is omega L and minus 1 on omega C. The impedance, putting the two of them together, the resistance and the reactance. So when we talk about a resistor, its R value is given in ohms. When we talk about a capacitor, its capacitance, that C value, is given in farads. And when we talk about an inductor, its inductance, the L value, is given in henries. And then there's some inverse units. Inverse of resistance is conductance, inverse of inductance is reluctance, inverse of capacitance is elastance, and they have various units. In this course, the resistance ranges you're probably going to see are more likely to be 100 to, I don't know, maybe 1 mega ohm. The capacitance values in this course, probably, I don't know, about 10 picofarads to maybe 100 microfarads. And I'm not sure about the inductors. I think it's more likely, let's try that again. Let's say 1 microhenry up to about 500 millihenries. Probably not nowhere near 500 millihenries. If you see, so this is still pretty small, right? But supercapacitors are in the range of about 5 farads. Right, so they can store a lot of charge. They may not store much energy because they may only be 5-volt devices. But in this course, it's more likely to be. I've forgotten what these ones are. I think they're... Oh, these are 25 volt, and these ones are actually 100 microfarads. And Oh, I think that is a... I've forgotten how to read these. They have a bizarre way of... I think it's 47 picofarads, but I'd have to look it up. Right, so that's probably in the sorry, probably nanofarads actually. Probably in the nanofarad range, that's in the microfarad range, so there's a factor of 1,000 between them. Okay, so now you know 95% of the course. What we're going to do next is we're going to go through and do some examples of mesh analysis, nodal analysis, superposition, Bevan and Norton, but we're going to do it all with complex values. Okay? Let's take a break. Let's make it a 15-minute break, and I'm going to get some coffee. Any questions so far? Okay. Thank you. Yep. Let me just turn off my mic so we're not broadcasting. Testing, testing. Testing, testing, testing. There we go. So in the vein of showing memes in class, I've been stealing stuff from Professor Broderick's meme channel, and so this is a way to remember what happens with a capacitor, right? If you've got DC, it gets stopped by the gate. But if you've got AC, it manages to get around it. Obviously, that's not the way it works, but it's just a way to remember that AC passes through the capacitor, but DC doesn't. It's not going to be too relevant to what we're doing right now, but when we start talking about transients, transients are all about what happens when you go from DC to some other condition. And you'll need to know how the capacitor reacts to DC. All it does is, if you've got V volts across the capacitor before the circuit changes, I equals C dV dt, you've got V volts after the circuit changes. It might change after that. Anyway, so I've started to put together the final, and I'm aiming to have 5 explain the meme 1-point questions on the final. Okay, so partly it's I don't like giving points for coming to class, but at least I've given you an explanation, given an explanation to the class about this, and you're here, so hopefully you'll remember. And it's just bonus. They're just 1-point bonuses. Not think I'm aiming for a 4 or 5, so you might get another 5 marks on the final if you can remember all the memes. But yeah, I think it's kind of fun, and it is actually relevant to the course. So we'll come up with a couple of others as well. Okay, before I get stuck into some examples, let me just fire up MATLAB so we've got it available once it's here. Okay, can put that into the background for now. So here's an example circuit. It's got a 1 kilo ohm resistor, and it has a 100 millihenry inductor. We've got an input voltage, VI, so that's the input voltage, and we've got an output voltage, VO. which is the voltage across the inductor. So is Liam here? No? Sonia Lee. What do we do? If R was a resistor and L was a resistor, what will we do to find the output voltage, VO? And if the VI was just 10 volts, so. Okay, yeah, that'll do. Right, so you'd add the two, I'm going to use the word impedances, but they're resistances. You'd add the two impedances R1 and R2 together. You'd figure out what the equivalent impedance is, and that would allow you to calculate the current. Once you've got the current, there's only one current flowing through there, so you can just multiply the current by R2, and yeah, that'll get you the output voltage. We do exactly that, except now we've got to think about impedances rather than, right? So we've got ZR equals 1000 ohms. Now the trick is making use of the frequency, the omega we're given, in order to find ZL. Right, so ZL equals J omega L. So we know L is 100 millihenries, so 100 by 10 to the minus 3, or 0.1 henries. And we know omega is 10,000. Right, so our ZL is J times 10,000 times 0.1. Right, so this one is here, and this one is here. Once we do that, once we've made the only use of the frequency that is helpful, we can forget about it. And what I mean by that is we can then write VI as being 4 angle 45 degrees. Right, we can write it in polar form. So let's do what Sonia Lee said, and we're going to find our equivalent impedance. And let's pick on someone else. Is Alex here? Yeah, Alex, can you tell us how we find the, well, if we had R1 and R2, what would be the equivalent resistance, and then if you can infer what that means for our, what's the, right, yeah, exactly. So we just add ZR plus ZL because they're in series. Right, so that's, and I didn't finish my working here, that's just going to be J1000. And if you want to be pedantic about it, you can write the units there as well. It's probably a good idea. Okay, so there's our equivalent resistance, or impedance rather. And I'm not going to write it as I of t, I'm just going to write it as small I. Right, remember V equals IZ is the impedance version of Ohm's law. V equals IZ. V equals IR, the impedance version of Ohm's law. Right, so our I is V on Z. So our V is for angle 45 degrees, and our Z is 1000 plus J 1000. And that's going to be in amps. Now we've got a slight problem. We've got the numerator in polar form, and we've got the denominator in rectangular form. One thing I didn't mention is that about complex numbers is if you're adding them, it's best to use rectangular form, but if you're multiplying or dividing, it's best to use polar form. Right? So if we have R1 angle theta 1 times R2 angle theta 2, that's just equal to R1 R2 angle theta 1 plus theta 2. And if we have A plus JB, let's go A1 plus JB1 plus A2 plus JB2, then that's just A1 plus A2 plus JB1 plus B2. Similarly, for subtraction, it's best to use rectangular form. Similarly, for division, it's best to use polar. The only difference is we subtract the angles and ratio the magnitudes. So I've got my voltage in polar form. I'm dividing it by another one, so I probably want to convert the other one also to polar form. So let's have a look at that. Right, so 1000 plus J1000, that's an angle of 45 degrees. Right, and a magnitude of square root of 1000 squared plus 1000 squared, which is 1000 root 2, I believe. Right, so our I equals 4 angle 45 degrees divided by 1000 root 2 angle 45 degrees. So I think that's just 2 root 2 on 1000, or root 2 on 500. Right, I'm going to subtract the 45 from the 45 to get an angle of 0. Let's just see if we can do that here. Right, so it's, now, how do I do it in MATLAB versus how do I do it in on your calculators? The reason I suggest you set your calculators to be using radians is because then you can just do something like this. Right, so there's the exponential form of 4 angle 45 degrees. Pi on 4 is 45 degrees in radians. I need to do exponential I or J times theta. Well, let's just do it that way, right? The nice thing about MATLAB, in fact, you can do this in your, if you're using your calculators, you can do polar form in the numerator and rectangular form in the denominator. Oops, what did I not do? I forgot to close the bracket. Let's try that. Okay, and let's just do format long so we can see more significant figures. Right, and that looks pretty close to 2 root 2 divided by 1000 for the real part, and it's zeros all the way down as far as the format long is concerned for the imaginary part. It's got a minus sign there, but there's not much there. Do you really want to see it? I think there is a MATLAB function called imag, and that's pretty close to machine epsilon, so the limit of machine accuracy. The equivalent for the real component is just real. Okay, here's another one. Any questions about that first one? Yeah? So is it what an acceptable final answer? Yep, that's perfectly acceptable. In general, not too finicky about whether you give the angle in degrees or radians, but just so long as you're clear whether you're using degrees or radians when I read it. Yep. Oh, sorry, you're right. We didn't finish the question, did we? Right. So we've got the current. Thank you. Right. So the question is after what is V out. So let's do that. So then V out is just V equals IZ. So we've got root 2 on 500 times ZL. Right? So ZL is root 2 on 500 times J 1000, which is just coming from here. So I think I can just, so it's J 2 root 2. Okay? And again, the units of complex impedance are ohms. Okay? Sorry, I don't know why I'm doing that. You're right. I am being silly. Thank you. Right? V equals I. The output is in volts. In this case, I'm okay with just leaving it as J 2 root 2. You could also write it as 2 root 2 angled 90 degrees volts, or 2 root 2 angled pi on 2 volts. Generally, if it's got a real part and a non-zero real part and a non-zero imaginary part, I want to see the angle. Right? Angle can be in either radians or in degrees, just so long as if it's in degrees, you put the little degree symbol up there. Sorry? So there's a J, right? So it's going straight up in the real and imaginary plane. So the angle that it makes with the x-axis is 90 degrees. Okay? Okay. So here's another example. Actually, just before we go on, let me talk about this one again. Another way we could have approached this one. Let's go with an orange pen. Another way we could have approached this one is as a voltage divider, right? So we could have said V out equals ZL on ZL plus ZR times V in. And that would give us exactly the same answer because the working's the same, right? We've got to find the equivalent impedance for the two in series. So V1 on ZL plus ZR is our current, and then we just multiply by ZL to get the voltage. But we do it in one hit. We just use the voltage divider equation directly. Either is fine. They both get the same answer. The reason I bring it up is this is a circuit that you could think about using the current divider equation, right? So we've got a current source and we've got a resistor in parallel with a capacitor. So, but we could do exactly the same thing. We could find, first of all, the equivalent impedance of ZR in parallel with ZC, and then we could find the voltage drop across, right? V equals IZ, and then we could just find I out by saying, by saying V on ZC to get its current. But let's do it the equivalent impedance way, and then I'll talk about the other way. Right, so our equivalent impedance this time is ZR in parallel with ZC. Now we've got to look at our omega. Omega this time is 1,000. So our ZC is, which is 1 on J omega C, is 1 on J, omega is 1,000, times 1, and it's microfarads by 10 to the minus 6. Now, one thing that's a bit odd about capacitors impedance versus inductors impedance is that capacitors impedance tend to have a negative sign out the front. Right? I've got a 1 on J there. I can write 1 on J as negative J. Right? Multiply top and bottom by J. I get a J on the top. I get a minus 1 on the bottom. So I get a minus J. So that's going to be equal to 1 on j by 10 to the minus 3, which is minus j 1000. And again, units of ohms. ZR is just 500, so that's easy. Let's see if I can pull somebody else. So Beata, how do I find ZR in parallel with ZC? Yeah, exactly. Right, so I'm just going to write it all on one side, so it's right, Z equivalent for ZR in parallel with ZC is 1 over ZR, 1 over ZR plus 1 over ZC. The other way to write that is that way, but I tend to avoid that because it makes you think you can write down the equivalent impedance of 3 things in parallel in a similar form. You can, but it's really complicated. And it blows up if you've got 4 things or 5 things. So I tend to avoid doing it that way. It's okay if they're just 2, but I tend to just use that one. Okay, so that means our Z equivalent is 1 on 500 plus 1 on minus j 1000. Right, which is 400 plus j 200 by the looks of things. And again, excuse me, units of ohms. Yeah, it's up. Yeah. Isn't the j negative? So here this follows, and then when I went from here to here, I've got minus j 1000. Right? So I just put minus j 1000 directly in for ZC. Is that, oh, you mean in MATLAB? Yes, you're right. Sorry. I should have put a minus sign there. Yeah, okay. And that's going to change the sign. Thank you. Oops. Right, so that's going to be a minus sign. Thank you. Okay. So there's our Z equivalent. So then we can figure out what VI of t is, right? It's just going to be II of t times Z equivalent. Now we haven't figured out what II of t is in, so it's 400 angle minus 30 milliamps, or 0.4 angle minus 30 degrees amps. So then our VI is II Z equivalent, which is 0.4 angle minus 30 degrees times 400 minus J200. Now, I'm going to just type in 30, but I'm going to convert it to radians by multiplying by pi on 180. While I'm here, if you're using MATLAB or even on your calculators to do this, the biggest mistake you'll make is leaving out the I or the J. Right? If you leave out the I or the J, the number is either going to be really, really tiny if the number is negative, or it's going to be enormous if the number is positive. So if you see really, really big numbers coming in or really, really small numbers coming in, go back and check that you didn't forget to put the I in. Okay, so what's that? That is 98.56 minus 142.28. 98.56 149.3. Okay, we're still not quite there yet. We need to figure out what I out is, and that's the input voltage divided by ZC, which is 98.56 minus J 149.3 divided by minus J 1000. So it's 0.1493 and 0.0 or 149.3 milliamps plus J 98.56. Units of milliamps. So just like the last example, I could do this using a current divider instead of a voltage divider, but a current divider. And I could have just written it out exactly the same way, but the impedance in the other branch divided by the overall impedance. I did it using, first of all, equivalent resistance to find the voltage drop, and then Ohm's law to find the current, and then the current times the, to find the voltage drop, and then the voltage drop divided by the impedance of the device we're looking at to get the output current. The previous two examples, I gave you omega. Sometimes I won't give you omega, I'll just give you the impedance. So this next example, you can see, just gives the impedance of C as minus J4 and L as J2, and there's no frequency. The only reason you need to know the frequency is if you're only given the capacitance or the inductance in farads or in henries. So Michael, how do you think you'd approach this question? Let's just change the capacitor to a resistor, change the inductor to a resistor. Just think about it that way at first. Yeah. Well, you could certainly add. Yep. So I'm not sure what the best. I'm just thinking what the best way to approach this one is. You can certainly combine ZC with R2, right, to just get one impedance in the middle branch. And then after that, so this is where I'm going to start not asking you how to do something, or not telling you how you should do something. Right? So the tools we have are mesh analysis, nodal analysis, superposition, Thevenin and Norton or source convergence. Right? So we could certainly think about nodal analysis, but we get a freebie on the VS side, right? Because there's a node there that's connected between the reference and the top node on the left of R1. But we've got a current source. Sorry, and we've got a current source. So maybe nodal would work. Mesh analysis might also work because we've got a current source and we know that can be problematic with mesh analysis, but it's only touching one of our mesh currents, right? So that means we get a freebie. So maybe mesh analysis could be used. Let's just think, let's go back and let's think about nodal analysis. So there's a node, there's a node here, there's a node here, there's a node here, and there's a node here. We get one freebie, but that still means if we did nodal analysis, we get 3 unknowns. So we'd end up with a 3x3 problem, which if we're using a TI-83 ends up being a 6x6 problem. Right? Which is not undoable, it's just a bit of a pain. So let's think about mesh. Mesh analysis. Well, there's only 2 meshes, but we get a freebie because of the current source. That I2 is the only mesh current flowing through IS, and I chose I2 to go in the same direction as IS. So we've got one unknown. So that's looking pretty good. That means we don't need to use matrices. We can just use algebra. So the other one I'd think about, with orange, is superposition. Right? And in superposition, I get some benefit because if I replace my IS with its ideal, right, it just gives me one loop. The L goes out of the equation and I'm just left with VS, R1, R2 and C. But then I also have to think about keeping IS and replacing VS with its equivalent, ideal equivalent, which is a wire. Right, so that one, I don't have to use any matrices. I can just do a current divider and then Ohm's law to get V out. So that one's probably got 2 problems. So I would probably go with mesh analysis for this one, right? Just because it seems to be the simplest approach. Right, so I2 we can write down directly as 4 angled 90 amps. And then the KVL for I1, and then it's plus 4 I1 minus J4 times I1 plus I2. Alright, I1 and I2 are flowing through the capacitor in the same direction. They're also flowing through the R2. R2 is 2 ohms. And that whole thing equals 0. Let's just write that out. Minus 12 plus 4I1 minus J4I1 minus J4I2 plus 2I1 plus 2I2 equals 0. Now I'm going to take so that becomes J4, that becomes J4. So that's going to be 6 minus J4, distributing and grouping like terms, times I1. So I think that means that one means that I've counted for that one, and that one. So then I'm just going to say, because everything else is a constant, so I'm going to bring the 12 over this side. And then that's plus J4 times J4. And then, so that's that one. And then plus well, 2J4, which is just J8. So that equals 12 J4 times J4. Yeah? The 2J4 is, you're right. Thank you. Right, so that's negative, that one's positive. Yeah, that's correct. Thank you. So then it's this ends up being minus 16. This ends up being minus J8. So that's minus 4 minus J8. So our I1 equals minus 4 minus J8 divided by 6 minus j4. Sorry? So because j times j is the square root of minus 1, so j times j is minus 1. Okay. And let's just so minus 4 minus j8 divided by 6 minus j4. Right, so that's 0.1538 minus 1.231. 1538. Minus j, 1.231. Okay, if you're working in MATLAB, there's a few other things you can do. I told you could use A tan 2, right, to get the angle. But there is actually a function called angle that will return the radians, the angle of the complex number in radians. And then the other one is the function ABS to get the absolute value, or the radius. So that's minus 82, 1.240, and minus 82.9. 1.240. $82.9. Okay. Next week. Sorry, yeah. Where I did the angle part. Okay, so the function angle will give you what's called the argument, the theta of a complex number. Okay, so but it gives you back the answer in radians. So I've had to convert it from radians to degrees by dividing by pi and multiplying by 180. Right, and then the other function is the absolute value, the modulus sometimes it's called, but it's the radius of the vector from the origin to wherever the complex number is in the xy plane. Right, so sometimes you write so you have a plus jb, and what I've been saying is r equals the square root of a squared plus b squared. But another way of writing that is the absolute value of a plus jb. That's where it comes, that's where the ABS comes from. Right, and then I've been saying theta equals a tan, we'll say 2 of b comma a. That also works, but in MATLAB it's just angle also works. The reason I prefer angle is in order to do the a tan 2, I've got to get the imaginary part of the number and then the real part of the number to feed it into a tan 2, whereas angle I just give it the complex number and it's straight away. Okay, so I'm done with my intro to this. What I'm going to do next week is get another tutorial problem, and we'll try and I might actually go back and do some more nodal analysis with just resistors in it, and then we'll do some other problems where we start bringing in capacitors and inductors, and we'll try superposition, we'll try mesh analysis, we'll try nodal analysis, we'll try Thevenin and Norton and source conversions with all of those things. I'm going to have another, this time just a 10-minute break, and then I want to talk about the lab I'd like you to do today. It's about superposition. It's a little complicated, but I'll explain why it's complicated. It's not that bad. It's just it's one of the one I find most students have problems with understanding what's happening. So I'm going to explain it, and we'll see how we go. But let's take it. Any other questions before we go on? Okay, let's take a 10-minute break, and I'll talk about the lab, and we can do the lab. After that, I'm going to grab some coffee. What's up? I did. I haven't put it up. I should do that. Yes, I haven't done that yet. Yeah, thank you for reminding me. Let's put those away. Yeah. So these chairs are falling apart. These things. Yeah, there it is. It fell off there. They're for whatever reason they've made these things. What this is a washer. They've made these things too big, so there's only a couple of threads, and so they're just by moving it, the screw falls out. So what the facilities guys have been doing, have been putting them up there, and eventually they come around and turn these things upside down, and then you get more threads coming out the bottom to fix these. But it's happening on all of them. Not really the best. want that one. Testing, testing. Okay, so let's talk about the lab. So the lab is meant to demonstrate superposition. And I mentioned earlier that there's a problem with it, right? So this looks pretty straightforward. There's three resistors, there's a voltage source, and there's a current source. Problem is that we only have voltage power supplies. We don't have current power supplies. So what you're going to have to do is analyze the circuit to figure out what value of voltage you need in order to produce IS. Right? And then set one of the power supplies up, both of which are going to be voltage supplies. Set one of the power supplies up to generate that particular voltage. But it gets worse, right? Because we're doing superposition. So you're going to have to construct three circuits in the lab. There's the circuit fully formed there's the circuit replacing the current source with its ideal, which is an open circuit. That's pretty easy. There's the circuit where we replace the voltage source with its ideal. So that's just a short circuit. The reason it's worse is because even though the current flowing out of IS is the same, the voltage is going to be different. Right? You're going to have to calculate that voltage at least twice, once for when in the whole circuit and once when you're replacing Vs with its ideal. And they're going to be two different voltage values. Okay? So what I think the best approach to this is going to be to get your three resistors, measure the three resistors, then do your analysis on the three resistors with the known values. Then you'll be able to tell what the voltage has to be for the full circuit and what the voltage to represent IS has to be for the replacing Vs with its ideal circuit. Okay, does that sort of make sense? Right, so there's the first part is to just redraw the circuit with the voltage supply only and the current supply only. Then calculate the voltages and currents for R1, R2 and R3 for the voltage supply only, and then the same thing for the current supply only. And then figure out what all of the individual values are based on these numbers, the V1s and V2s, at I1s and I2s, and then actually figure out what the numbers are. And then there's a couple of other questions there. I'm also asking you to go around the different loops. There's the left mesh, the right mesh, and then going around the outside, making sure everything adds up. You don't have to do LT spice today, that can be part of the write-up. But again, you do the same thing with the write-up, and I need you to construct the circuit, the three circuits, both just the voltage source, just the current source, and measure V1, VR1, VR2, VR3, IR1, IR2, IR3 for those three circuits. So it's a lot of measurement, and the tricky part is getting that voltage source to pretend to be a current source. Okay, any questions? Make sense? The circuit's pretty simple. Like I said, the only complicating factor is figuring out what voltage to use here. So let me get some resistors out of there. I'll get 3 different values of resistors. You're going to have to choose your own. I don't know whether it specifically says what voltages to use. I don't think it does. So 10 volts, does it? Oh yeah, it does. Okay, so 5 milliamps. Very good. I should put that procedure on the start of the procedure on the next page, just to make it a bit clearer. And yeah, I'll see if I can get those values. I think I should have all of them. I'm just trying to remember. Oh, that should be okay. I just remember one of these. I don't think it was this one. Some of the resistors got a bit hot, so I don't think it was this one. That one's only going to, even with the I squared R on the R1, it's only 0.0 something. What was it? 0.03 watts. So that should be fine. Okay, let me grab some resistors. By the way, 1200, 270, and 560. 270, 560, 1200. As always, just be careful that they are what they say they are, right? And so let me just write it down. So this one is brown, which is 1, red, red. This one is red, purple, brown. And this one should be green, blue, brown, I think. So there are some resistors, I'm trying to pull them out, but that don't match the label on the boxes. So yeah. It just makes life a little easier for all the analysis. Okay, so grab the resistors and measure them first. They're going to be, I think they're 10% resistors, so they're going to be within 10%. But it's just nicer to get the actual value. And I'll go open up next door in case anybody wants to use that. Okay.